Okay, so we'll start our second unit, Laplace transform. Weightage of each unit is roughly 22 to 25 marks because we have 4 units in our syllabus. We completed numerical method. Now we started this Laplace transform here. This is again a very simple topic that you have. Easily you can get the marks on Laplace transform also. So agenda for the first session here. First we'll learn about what is the need of this Laplace transform, why it is required. Next, we'll see the definition of Laplace transform. Then prerequisite formulae that we require to prove the Laplace or to find the Laplace of a standard function. Mainly we have some integration formulas that we require. Next, Laplace transform standard function will calculate. So these are the 4 points. We'll do it today only. Okay. So first and most important thing that you should know why there is a need to learn this Laplace transform, because obviously the first use that we have is it is mainly used to solve the ordinary differential equation, and this is the part of our syllabus. We are going to use the Laplace transform to find a solution of ODE. Already you learnt one method, yes, or one way. What is that method to solve the ODE? Yes, it's a numerical method. Is that in numerical method you learnt Euler's method, RK methods to solve the ODE, but that is approximate method. Here you are going to find the exact solution of the differential equation by the help of a Laplace. So that is first application, but it is already a mathematical application. If you see the other applications, actually this Laplace transform is widely used in physics, electrical engineering, control engineering, optics, and signal processing. So out of that, probably if the courses of control engineering and electrical engineering that is in your next semester you will definitely going to use the Laplace again there. Okay. But one of the major area of application of Laplace is the signal processing. In signal processing, actually, the signals are transformed in the frequency domain with the help of Laplace. There are two types of signal. One is a time signal and another is a frequency domain signal. And when we transform any time domain signal to the frequency domain, we can find out at which instant which frequency is occurred and all that other things. So we can analyze the data we can analyze the signal with the help of Laplace transform there. So that are the applications there. Don't go in the detail because these applications are not right now in the same two here only. Only one application, that is solving the ODE, that is mathematical application, is a part of our syllabus. Okay, clear? Uh, any issue in getting why this Laplace transform is required?
No, sir.
So come to the first thing. We have the definition. The definition of Laplace. Definition of Laplace is on the screen. So you will observe it is denoted as, or you can read like L is a Laplace operator. It is like a differential operator. Laplace of f of t. You can read like Laplace of function of t. Okay, is function of s. So it is new function we denoted f of s. You will observe another important thing. These two functions are different. So suppose small f of t is algebraic function, not necessary capital Fs is again algebraic. It can be a trigonometric, it can be exponential. So function will change completely. So we are transforming the function of t to the function of s with the help of this integral. This integral is known as Laplace of the f of t. What is the definition? Definition is integration 0 to infinity e raised to minus st f of t dt, where important thing is the function should be a bounded function for t greater than or equal to 0, or indirectly I will say the function should be defined for t greater than or equal to 0. Now, because of this condition only, there are very limited functions whose Laplace exists. Very limited functions are there. Can you tell me at least one function which is not defined on the interval t greater than or equal to 0? Anyone? I want one simple single example. Actually, there are many examples, but I want just one example from you. A function which is not defined on the interval t greater than or equal to 0. It does not exist or does not define. Yes, quick.
Exponential.
Exponential function exists now. If you see the graph of e raised to x, the graph of e raised to x exists from 0 to infinity. It is exponentially increasing.
So minus x square.
Minus x square. Minus x square, yes, good. Because why minus x square? Because you take minus x, not minus x square. I will. You should say x raised to minus 2. Okay. Because minus x square exists. Minus x square graph you can draw it. Okay. It is just maybe on the negative side. You're not getting the question actually. The question is we should have the function which is not exists for t greater or equal to 0. There are very simple functions like tan. Why tan doesn't exist for t greater than or equal to 0? Can you tell me a single point where the function is undefined, it is unbounded? Yes, at which point the tan is unbounded? Tell me.
So pi by 2.
Pi by 2, yeah, tan pi by 2, pi by 2 is greater than 0, pi by 2 is greater than 0. So tan pi by 2 doesn't exist, so it is unbounded. As it is unbounded, Laplace of tan does not exist. Okay. Similarly, sec. Where is the sec function doesn't exist? Again, pi by 2 is it? Because sec is the reciprocal of cos. Cos pi by 2 is a 0. So sec pi by 2 doesn't exist. Cosec 0. Next, if you come to the cosec 0, this cosec 0 doesn't exist. Cot 0 doesn't exist. Log 0 doesn't exist. 1 upon 0 doesn't exist. 1 upon this is when t is 1. When t is 1. Like that. So there are infinitely many functions you can create of this type mainly. Where denominator for one particular value of t, the function is unbounded. If the function is unbounded, remember Laplace does not exist. So the best part for us is now, like a derivative, there are very limited in derivative. Yes, derivative of all these function exist. Okay, but Laplace of this function does not exist. So there are very limited function. There are very limited function whose Laplace exists. Got it? So that is the first and important thing, that Laplace of which function exists then? Hardly sine and cosine only. Sine and cosine. Then exponential. Then x raised to n, where n is a positive. And sine hyperbolic and cos hyperbolic. So there are 6 to 8 formulas only that you have to remember later on to get the Laplaces there. So that is the one thing. Let I show you what exactly happens when you take a Laplace of some function of t. So can anyone tell me this graph represents of which function? What is the function there?
Y is equal
Y is
to
equal
x.
to x.
Correct. Good.
X.
Y equal to x. So I will say here it is y equal to t, because why generally we use this one, y is equal to t. This t and s, this is a t is for the time domain. So in general, the t variable is used because our function is in a time domain t, and this s indicates a frequency, or sometimes in some author are using, instead of s, omega is used. So the definition will change. Laplace of f of t become integration 0 to infinity e raised to minus omega t f of t dt. Okay, so that will be the definition. So if instead of s, omega is used, so that is just change of a symbol only, and this omega is used because of the frequency. But throughout the topic we are going to use s only. So if we apply this definition, to the Laplace of t, we get 1 by s square. We are going to prove it. We'll prove it. Okay, right now only. So you will see the graph becomes like this. This is the graph. This is the graph of 1 upon s square. So you will observe the nature of the function is like y equal to t in the t domain, while in the frequency domain the graph becomes like this. Okay, both t is greater than 0 and s is also greater than 0. So only that part we are taken here. So that way the graph is shown here. So the function is completely changing, and because of that this notation occurs. So function of f of t become a function of s, but they are not same f. Okay, they are not same function. The functions is completely changing. It is a transformation of one function to some other function there. Got it? Got it?
Yes, sir.
Okay. So come to the next part there. Now you will find some prerequisite formulas. You will have integral of e raised to x is e raised to x only. Integral of x raised to n is x raised to n plus 1 upon n plus 1. These are the two formulas that are also useful to prove the standard result. Integral of e raised to x into sine bx is e raised to x upon a square plus b square a sine bx minus b cos bx. Similarly for cosine, these prerequisite formulae you already learned in the last semester, okay, and that are the few formulas we require it again. So up to the Eilert rule. So these are only 5 formulas are enough. These 5 formulas are enough to get the proof of the standard result as well as type 1 examples. So only in type 1 we require a little bit integration formulae. Later on, nowhere integration formulas you require. Got it? Okay.
Yes, sir.
Okay. So this is the last part of the today's session. Here is a list of standard results and their Laplace transform. The Laplace of 1 is 1 by s. Laplace of e raised to at is 1 upon s minus a. Laplace of e raised to minus at is 1 upon s plus a. Now these are 4 results and these 4 total 8 maximum results that you have in your syllabus. So that you have to remember. That you have to remember to solve the examples later on, because nowhere we are going to find the Laplace by definition later on. It is just like a derivative. When I ask you what is the derivative of x raised to n, you directly say n into x raised to n minus 1. You're not applying the definition there. So that way we are going to find the Laplace later on. But before that, yes, you should know how that formula occurred. So that derivation we are going to complete it today only. So these 8 proofs will complete it right now. And that is a part of your syllabus also. These proofs can come for 2 marks as a 2-mark question. So let me start the first one. The first one is say find Laplace of 1. Suppose the first property that we have. What is the Laplace of 1? So we have to just apply the definition. Nothing is in our hand except definition. We start with the definition. By definition, what is the Laplace of 1? Yes, integral. Yes, anyone?
Reducing minus xt.
What is f of t here? Into f of t is there, na? So what is f of t here?
1.
1. So f of t dt. So this way you have to start the proof. By definition of a Laplace, Laplace of 1 is integration 0 to infinity e raised to minus st. That f of t should be here and into dt. So this f of t is 1 here. Now, yes, we want integral of e raised to minus st. Yes, anyone? What is the integration of e raised to minus st?
Minus s.
Minus e raised
E raised to minus st upon minus s, is it?
to minus 1.
Put upper limit. Now, 2-3 things you require throughout this topic. That is e raised to 0. What is e raised to 0?
1,
What is
1.
e raised to infinity?
0,
E
0.
raised to infinity is infinity. E raised to minus infinity
Zero.
is tending to 0. So these 3 values, mainly the first e raised to 0 value and e raised to minus infinity value, that you require again and again throughout the Laplace there. Okay. When you put upper limit, that t is infinity, so e raised to minus infinity is a 0. For lower limit, there is a minus sign. When you replace 0, e raised to 0 is 1. So the final answer is 1 by s. Okay, clear? So Laplace of 1 is 1 by s. Got it?
yes sir,
Okay. So another important thing you will observe, when you replace this s by 0 or s by t by infinity and t by 0, you'll observe it become e raised to minus s into infinity. E raised to minus s into infinity. So this is when s is a positive, then only it become e raised to minus infinity and it is coming 0. Suppose s is a negative. If s is a negative, that negative become positive and e raised to infinity become infinity, this one. And then integral diverges. Then Laplace does not exist. So there is unwritten condition always, and that condition is here, s is greater than 0. There is no need to write this condition. These conditions are everywhere in each formula. Okay. So just like t greater than 0 is there in Laplace, Laplace of f of t exists for t greater than or equal to 0 if function is bounded. Similarly, fs exists here for s greater than 0. Is it clear? Is it
yes
clear?
sir.
Okay. So this question can come for 2 marks there, 2 marks in the final exam. Okay, this is a very small question. So that about first result. I will show you the next then. Are you completed?
Yes, sir.
Okay, second result. So we take Laplace of e raised to at. Say Laplace of e raised to at by formula. Yes, tell me. Integration. Is it?
Yes, sir.
Tell me the next step. What should be the next step?
Sir, adding the powers.
Yes, base is the same, so we'll add the power. But while adding the power, we'll keep one important thing. Keep a minus outside. The reason is there. The reason is here because we want e raised to minus infinity there. When we replace t by infinity, it is minus of s minus a into infinity. So e raised to minus infinity tends to 0. Then only the Laplace exists. And we can say s minus a should be greater than 0. Obviously, that s minus a should be greater than 0. So that is the unwritten condition there. And now the integration is here e raised to minus of s minus a of t upon minus of s minus a. That about integration. Limits are 0 to infinity. As usual, upper limit e raised to minus infinity is a 0 because this minus sign is there. Minus sign is there in the bracket. So this minus sign is very important. Lower limit have the minus sign, but t is a 0. E raised to 0 is 1. And the final answer is what it? So that is the end of the proof. Laplace of e raised to at, you should remember now, it should be 1 upon s minus a. 1 upon s minus a there. Clear?
Yes, sir.
Okay. Done? Can I show the third then?
Yes, sir.
Okay. So third is very simple. In third, there is a small change only. So let I take this one. So Laplace of e raised to minus 80. This is the third one. Laplace of e raised to minus 80. So here should be a minus sign. E raised to, so we want minus should be outside. So it is s plus a. Got it? Got it? That's the end of the third property. Is that clear? What is the Laplace of e raised to minus 80 then? Laplace of e raised to minus 80 should be, yes?
1 upon s
One
plus
upon
a.
S plus
Okay,
A.
1 upon s plus a. Correct. So that about the third result. Is that clear?
Yes, sir.
So can I show the fourth then?
Yes, sir.
Okay. So the fourth is a different now. It is a Laplace of t raised to n. It is a completely different Laplace of t raised to an algebraic function now. So we uh, integral 0 to infinity e raised to minus st f of t is in this case t raised to n. Now, can you tell me how to integrate now? Yes, how to integrate? Quick, quick.
Value.
Pardon?
So by using by parts.
By using by parts. Not correct. Yes, you thought about product and by parts. That's okay, but it is not a by parts. You can observe this integrand have some special thing that you've
Sir,
seen before.
sir. Sir,
Yes.
E is to
Pardon?
X into E is to X.
E raised to x. You want to convert it. Why? No. Can you compare this with the definition of a gamma function?
Sir, gamma function.
Yes, we should convert in a gamma. So either go for substitution as st equal to x, or you recall that property integration 0 to infinity e raised to minus kt t raised to n dt. So can you recall directly property? Then you can write it directly. If not, you can put st equal to x and complete it. So which one you want? Direct or you should go by substitution. You want to go by substitution. Yes.
Sir, by substitution.
Pardon?
Sir, by substitution.
Substitution you want. Okay. So if you want substitution, you should start with let st equal to x. If st is x, this t becomes x by s, and this dt become dx by s. You will observe the limit remains unchanged, because when t is a 0, s is a 0, sorry, x is 0. When t is infinity, that x is infinity. So it becomes e raised to minus x. The value of t is x upon s raised to n, and this is a dx upon s. So all these values were replaced there, and we got here, this part is just substitution there, and you will observe 1 upon s raised to n plus 1 comes common. This comes integral 0 to infinity e raised to minus x, x raised to n dx, and this is the gamma function. So its answer is a gamma n plus 1 upon s raised to n plus 1. That is the end of a question. But we keep in gamma form provided n is a fraction. If n is fraction. But suppose n is integer, then gamma n plus 1 can be written as n factorial. Got it? That's the end of a proof here. Is that clear?
Yes, sir.
Yes, sir.
So once you complete, tell me. I will move to the next property then, fifth one.
Yes, sir.
Okay. So come to the fifth property here. The fifth is now only trigonometric and hyperbolic left. Last four, two are trigonometric and two are hyperbolic. And if you done one proof now, remaining three are exactly similar. I will show you. So come to the Laplace of sin 80. Laplace of sin 80. By definition, it's integral 0 to infinity e raised to minus st sin 80 dt. Can you tell me how to proceed now? One of the way is obviously the by parts, but by parts will be a lengthy. Instead, we have that standard formula, integration of e raised to ax into sin bx dx. So that formula just I shown you. Okay, so if you use that formula, integration of e raised to ax into sin bx dx is e raised to ax upon a square plus b square. In this case, b square is this. A is a minus s and b is a there. So a sin bx, sorry, a is minus s. A sin bx, that is sin 80, minus b 0 to infinity. Got it? Is that clear?
Yes, sir.
This is by formula only. Now put upper limit again. It become e raised to minus infinity. E raised to minus infinity is a 0. That's for upper limit. Lower limit of the minus sign. E raised to 0 is 1 upon s square plus a square. So this is where putting s by t by 0. So e raised to 0 is 1. Now if t is a 0, what is the sine 0? This sine 0.
0.
And what about cos 0?
1.
1. So what is the Laplace of sin 80 then?
Plus a upon s.
Okay. So that about Laplace of sin 80. So this is the fifth result that you should remember. Now I will just modify this to get hyperbolic. This is sixth result, sin hyperbolic 80. See, sin h80. If sin hyperbolic 80, then integral 0 to infinity e raised to minus st sin hyperbolic 80 is there. Okay. What is the difference in the formula of sin 80 and sin hyperbolic 80? In that this is a minus only. This is minus only. All other things are same. Where this become only sin h80, cos h80 there. Okay. Then sin hyperbolic 0 is a 0, cos hyperbolic 0 is 1. So all that things remain same. This is only minus there, and your final answer comes a negative there. minus here. So final answer is a upon s square minus a square. Got it? Laplace of sine hyperbolic at is a upon s square minus a square. Is that clear? Is that clear? Okay.
Yes, sir.
So remaining two, I will give as a self-study, where Laplace of cos at and Laplace of cos hyperbolic at is exactly similar to this. So already I shown you the formulas. Here are the formulas. So this is the Laplace of sine at we seen as a upon s square plus a square, and Laplace of sine hyperbolic at is a upon s square minus a square. While Laplace of cos at becomes s upon s square plus a square, and cos hyperbolic s upon s square minus a square. So these two are similar. These two are similar. Okay, that way. So hardly there are only 8 standard results there. See the list of differential formula. You will probably have the 10 to 15 formulas there. Okay, but in Laplace you will have just 8 formulas, and with the help of these 8 formulas now, near about entire unit you are going to complete it. So these 8 formulas you have to remember. Okay, these formulas, with the formulas now, nowhere we are going to do the integration after that. Okay, after the type 1 only. Directly we use these formulas to get the Laplace of the given thing. Clear?